So we're going to talk about how do we go from the physics that we were used to in our non-AP class to the physics we now have to deal with in our AP class. And the big difference, honestly, is calculus. All right, so I'm just going to set up how we used to look at things, and then I'm going to show you what that really means in a calculus world. So hopefully you can see that transition, you can see those links, and that way you can make connections to things that felt more comfortable to you from the past. So let's first start with the color here. So I'm just going to use our old kinematics friends, and I'm just going to focus on some basic ones. So we know that, say, velocity is equal to your total change in position over your change in time. And we said, well, that, by definition, is the slope of a... Why am I being an idiot today? An xt graph. All right. And then we said, well, another one of our basic constructs is acceleration. Well, acceleration is your change in velocity over your change in time. And so we said, well, that is the slope of a velocity time graph. Cool. And then we also said that you can use the velocity time graph again to get displacement. And this would be like the total displacement is equal to your total velocity times your time, which we said that was the area of a velocity time graph. All right. Now that's not the per se equation. That's just constant velocity. That's not for acceleration. So don't judge me when I go a little off the rails here. But this is kind of our basic. This is our basic structure. Now, since a velocity time graph encompasses both the slope and area, I'm going to use that as an example. Okay, so I'm going to draw a velocity time graph. All right, velocity time, sweet. And normally, if we did velocity time graphs, they'd be like, hey, I'm a line, yay. That would be the limit because, hey, slope is the area of velocity time graph, and then you'd have to do this calculation. And so you're like, well, okay, for acceleration, it's actually 1/2 velocity times time, because it was a triangle and all that stuff. So y is just vt. So we're going to get into that now. What does that really mean? Why do we really do that? But if you're taking AP, it's probably not going to be a straight line. It's really not. So let's get rid of that. And let's just, real basic example here. Let's just pretend that we're, have a nice upwards curve here, and that this line is described by the equation v equals 2t squared. All right, so we're just going to say, hey, look, now your velocity is not just, a pure number, and now it's represented by its own equation. And so that's where we have to really start using calculus. So using that as my example, I'm going to show you how we would actually find the same concepts of slope and area using this new calculus method. So that's the physics we know. Let's start talking calculus. So let's get blue going here. All right, so let's look at what this looks like in terms of calculus. All right, so now our velocity is going to be described by dx dt. And what this means, this dx and this dt, this right here are little pieces, okay? So this is like a little piece of your position. This is a little piece of time. And the reason why we have to deal with little pieces now is because we have to kind of look at this and say, well, I got to draw a nice line here. Sorry, I don't want thoughts. I want thoughts. So if I draw a nice line here and say, well, I have to have the tangent at that point, so I actually have to draw a tangent line. So I have to kind of zoom way in and then stretch that piece way out in order for that to make sense. So this is saying, well, this is an infinitely small piece divided by an infinitely small piece, and that's going to give us that super zoomed in version. Because as you know, a curve is made up of an infinite number of infinitely small lines. So, but again, fundamentally, that is equal to our slope, except it's going to be a slope at a point in time in this case. Okay, so it's going to be that tangent line. And if we then say, well, what's acceleration? Well, acceleration is dv dt. All right, because it's the small piece of our velocity at that point divided by a small piece of time. So again, it is still technically, fundamentally, very much similar to the slope, except again, it's the slope at a specific point in time. All right, so we're again zooming into that really specific spot there. Now, that means that we can say, actually get a value for this. So let's talk about the most common way that we're actually going to do that, and that's called the power rule. All right, so power rule for taking derivatives. Okay, so this is specifically derivatives. So basically what we're doing is we're saying, well, how do I get that equation that then represents all of those little tiny microscopic slices that we call little slopes? Okay, well, the power rule would be this. We'd go, okay, so we're going to change velocity into dv dt. All right, and so that's our acceleration, so that'll be our slopes. And so if we wanted to find the actual velocity, or I should say actual acceleration, my bad. So if you want to find the rate and change of your velocity over time, then you'd say, okay, well, let's take the derivative of this. Okay, so the derivative of this with respect to time would be equal to 2t times 2. All right, so you'd have 2t times 2. And so then that is actually equal to 4t. And you're like, Szymanski, how the heck did you get that? Well, here's the power rule for you. So when you want to take a derivative of something, it's going to, I'll just use the letter x because everyone loves x, it's universal. So let's say you've got x to the n. Well, the derivative of x to the n is n times x to the n minus 1. So here we said, well, x is our value of t in this case, and so we would take it, and then we would say, well, we're going to multiply 2t times the 2, all right, and then we're going to do to the power of minus 1. So that becomes 2n, because that was, like I said, our x, and then to the power of n, so we got to multiply it by 2, so that's where they become a 4, and then minus 1. So 2 minus 1 is 1, so 4t, that's our answer. All right, but this right here, this is your power rule for taking derivatives. And in all honesty, you're going to use that like 80% of the time when you take a derivative. Now, obviously, there's cosines and sines and logarithms and all sorts of other stuff, and that, you know, that'll come. But this is going to get you through the vast majority of stuff, okay? So that's how you take derivatives, aka slopes. The other thing that you're going to run into a lot is areas, okay? So if we look back here, areas would be like this area. And before it was real easy because it used to be like a triangle or a rectangle, but nope, now it's underneath a slide, I guess? I don't know. It's something crazy. So to do that, what we're going to do is we're going to add up all the chunks. So if you remember my class, I used to always give kids graphs that looked like this. So just a quick VT graph, and I'd be like, oh, look, there's an angled piece, and then there's a flat piece. And so what you had to do is you had to take the pieces of like part 1 and part 2, and you had to add them together. So you had to find those individual areas and add them together. Well, that's what we're going to do with calculus. Okay? So for calculus, we are going to integrate to find your area. So again, if I wanted to find displacement of a velocity time graph, I would have to get the area of a velocity time graph. And this would be the total area of a velocity time graph. So the way we do that is we integrate. So the symbol for integration is this. Okay, so we got delta x would be equal to this integration sign, which means basically it's like the sum of, all right, you're adding all the pieces together. And since it's velocity and time, it would be velocity with respect to time times dt. All right, so we're going to add up all the small pieces over time of this function vt. All right. So, well, what's vt? So if you remember before over here, our vt was, our velocity in terms of time was 2t squared. So we're going to integrate this. So that equals the integral of 2t squared dt. All right, so there's our equation. We replace the idea of velocity with the function that describes it. And so to take an integral, again, we're going to use the power rule, but this is going to be power rule for integrals. All right, integration. That's what we call it. All right, so power rule integration. So to do that, we are going to first, you take out all the constants out about, and then you are going to do the following. You are going to go, the integral of x dx is equal to, I should put an n up here, is equal to n x to the n plus 1 divided by n plus 1. All right, so if we apply that over here, I'm going to pull the 2 out because it's a constant. You pull all your constants out, and then I've got t squared. Okay, so x is my t, n is my number 2, so I'm really going to have equals 2 times x to the n plus 1, so that's going to be t to the third divided by n plus 1, so divided by 3. All right, and that's what gets rid of the dt as well. So then you can see that I really have then as my answer 2/3 t cubed. All right, and that would be equal to your total displacement. So I could say, hey, give me a time, crunch that in. I can then tell you exactly what my displacement would be at that time. So these are the two most important things. All right, you've got your integral rule, and you've got your integral rule, and you've got your derivative rule, both using the power rules. There's my brain. Wow, it's off today. All right, so then let's put this into an example. Okay, so this is just all the background. This is the filler. Let's actually do an example. So how do we actually use this in physics? Good question. New page. All right, so zoom way the heck. Come on, work. Why are you being like this? Oh my gosh. Technology, it does not like me. And yet here I am trying to use it. All right, so let's just do an example problem. Okay, so let's say that we have a velocity equals negative 10 x squared. All right, so you've been given this function. Our objective is to find x in terms of t. So find the equation that describes this, your position with respect to time. All right. So technically this is called differential equations because we are looking for an equation that contains not only the function but also the derivative of said function. But don't worry, you don't really need to know that. The goal though is in order to make this work, you have to have this one variable on each side. Okay, and the link between v and x and t, oh darn, we need a t, so we got to get t to show up. So check this out. We're going to combine what we know from our past with what we now know to say, well, velocity, which used to be delta x over delta t, is now dx dt. That's velocity. And that's equal to negative 10 x squared. So hey, now I got my x's, now I got my t's. So what I'm going to do is I'm going to just do some algebraic manipulation and rearranging here. And so just going to do this, going to dx over a negative 10x squared. You know, let's not do that. Let's just do this instead. We'll leave the negative 10 over there. That's what I'm going to do. I'll leave that negative 10 over there. All right, so divided by x squared equals negative 10 dt. Oh, I feel so much better. I hate having too much stuff in the denominators. All right. And then since I really just hate denominators in general, let's just change this into x to the minus 2 dx equals negative 10 dt. Oh, I feel so much better. All right, so now I can just kind of integrate both sides. You know, just like algebra, where you divide both sides and stuff like that. You just integrate both sides. So this side will be integrated with respect to x. This side will be integrated with respect to t, and we'll kind of see how it goes. So next line would just be say, hey, let's just integrate you bad boys. All right, now watch, I'm gonna put the integral sign in here because that is a constant. That negative 10 is a constant, so I'm not gonna mess with it. I'm just gonna pull it all the way out. So now if we use our power rule, remember our power rule says x to the n, if we integrate x to the n, dx obviously, is gonna equal x to the n plus 1 divided by n plus 1. So on this side, our n is now a minus 2. So we're going to have x, well, minus 2 plus 1 is negative 1 divided by negative 1 equals, and then this is a negative 10, and then the integral of dt, well, that's really just 1, okay? Or you could argue it's actually, so like if it's 0, it's a 1 here. So like 1 dx. In reality, that's x to the 0 dx. That's a t, Szymanski. Do better. There we go, dx. And so x to the 0, if we were to integrate that, you'd say, well, x to the 0 plus 1 becomes x to the 1 divided by 1, aka x. So there's your, derived, like, why is it this? Tell me. There you go, I just told you. So this just becomes a t. Cool, sweet, awesome. And so now I can just do a little more algebra. This nukes out that guy. So now I have x to the minus 1 equals 10t. And so quite frankly, it just depends on how deep down the rabbit hole you want to go, because you could also make the argument that this is then equal to, 1 over x is equal to 10t. You could 1 over 10x, blah, blah, how far you want to go. Now, there's one thing I've been skipping here, and if you're a math teacher, you've been yelling the whole time, and that's fine, but let's talk about the elephant in the room, and that's the fact that I lied to you guys already. You're like, wow, horrible teacher, already lied. Whenever you integrate something, there's a constant that should show up, okay? So really, there's this unknown constant that's going to kind of live off to the side, and it's going to show up. Now, I'm going to be 100% honest here. In physics, usually we can understand these constants through like logic, and a vast majority of the time, it is 0, okay? A vast majority of the time, it is 0. But it could be a case where it's not 0. And so just to make sure I'm covering all my bases here, you would have to be either given some sort of clear logic understanding or just some argumentative statement. So let's just solve for C so we are 100% done. But I'll be honest, 90% of the time, this is your answer. Like, you're done here, and then you can rearrange as you see fit. You really don't need the C, but maybe you do. Maybe you do, okay? So let's say you need the C. So in order to have that, you'd have to give another piece of information. So let's just say you were also told that the initial, at time 0, the position is, say, I don't know, 1/2. All right, so we're just making something up here. So then basically you'd have to then go into this function here that we have down here and use this 1/2. So at time 0, this equals 1/2. So you'd be like, okay, well, 1 divided by 1/2 equals 10 times 0 plus C. Okay, well, that goes away. 1 divided by 1/2 is 2. 2 equals C. Oh, cool. So then you can take that and you can slam that in there. And so then technically your final answer would be 1 over x equals 10t plus 2. All right. But I'm not going to lie. Everything that's in blue, that, and honestly, and in red, that is mostly just math class stuff, which could technically show up. But honestly, everything I did in black, that's the physics. Okay, that's that. So hopefully that wasn't too convoluted. Hopefully that helps you understand, what is integration, what's a derivative, how are we going to use them a little bit better. All right, well, as always, I'll see you guys in class.